Hi everyone, this is a quick bonus lecture. What I wanted to do is I wanted to come back to the mergesort recurrence relation. And I did mention a few times through the course of the main lecture that this is not a first order or second order recurrence relation. What it does is it relates the nth term in the sequence back to the n over 2 term in the sequence. And because it's not a first order or second order recurrence relation, we couldn't use our general methods of characteristic polynomials, finding roots, etc. to get our solution. So instead, we just modified or adapted our method of iteration for the first order recurrence relation, and it worked out in this case. However, when I said that you couldn't use the general techniques to solve this, well, that's not quite the full truth. We can use our characteristic polynomial to solve this kind of equation, but it does involve a little bit of creativity in how to get us to apply that. And so that's what I want to do in this bonus. I want to show you that you can use our general methods. So let's see how we would do this. So just a reminder, the recurrence relation we're interested in solving is Cn is equal to 2 Cn over 2 plus n minus 1. So that's the recurrence relation we're interested in solving. We also have the initial condition C1 is 0. And what we're going to do next is we are going to convert it to a first order recurrence relation. So what we'll do is we'll let, as we've done before, we'll let n be 2 to the power of k. So then, what does our recurrence relation become? Well, we get c 2 to the power of k is equal to 2c, and n divided by 2, that's 2 to the k divided by 2, so that's 2 to the k minus 1, plus 2 to the k minus 1. So what we notice now is that this recurrence relation is relating this quantity, think of it as a function of k, to the same function, but now k is 1 less. So it just relates one term to the previous term. So if we let a sub k denote c of 2 to the k, then a sub k minus 1 is just c 2k minus 1. So our recurrence relation becomes ak is equal to 2 ak minus 1 plus 2k minus 1. And that's a first order non-homogeneous recurrence relation. What does our initial condition become? Well, our original initial condition is c of 1. So I look at this initial condition, c of 1 is 0. But what is c of 1? Well, that corresponds to k being 0, because c of 2 to the k, in order to get this thing inside here to be 1, I need k to be 0. So that means we've got our initial condition for a0. a0 is, and maybe I'll just put these down here. What is a0? It's c2 to the 0, which is c of 1, which is 0. So this becomes our initial condition of a naught is equal to 0. So there we go. We have just taken our original recurrence relation, which we're interested in solving, and we've reduced it to this recurrence relation, which we are now interested in solving. And that's a first order recurrence relation. So now we solve this first order relation. And we can do that using our general methods. So we'll go ahead and we'll find the homogeneous general solution. So what's our homogeneous general solution? Well, the homogeneous recurrence relation is ak, and I'll bring the ak minus 1 to the other side, so minus 2 ak minus 1 is equal to 0. And the solution to that, or at least the general solution, is a sub k is equal to some constant times 2 to the power of k. So there's our, and I'll put a little superscript of h up there, there's our general homogeneous solution. Now we can go ahead and work on the non-homogeneous part. And in order to do that, we first find a particular solution. To find the particular solution, we have to come up with a guess. What's our guess at the form of our particular solution? Well, we look at the non-homogeneous part. The non-homogeneous part is 2 to the power of k minus 1. So what do we guess our solution should be of the form of? Well, it should involve, my initial guess is, well, it should involve some power of 2, like a 2 to the k. That accounts for this piece here. But, oh no, the homogeneous solution is already 2 to the k. So that means I will amend this and say, well, that's already a homogeneous solution. So what I'll do is I'll bump up and make it a k 2 to the k. And so that's my guess at the particular solution corresponding to this part of the homogeneous function, the 2 to the k. And now we'll use our undetermined coefficients. So I'll call this maybe a b times k times 2 to the k. Plus, and then the other part of the function f of k in this case is a constant. So I should add on to my initial guess some piece that's going to account for the constant. So we'll add on a c. And again, it's our method of undetermined coefficients. So I'm essentially making the guess that I've got a constant function, which is a solution, so like 1. And so this is the constant multiple of that. And so there's my particular solution that I'm guessing. Remember, this is the method of undetermined coefficients. Okay, so now we take this particular solution and we plug it in to the non-homogeneous equation. So my non-homogeneous equation is a to the k. So I'm going to take this thing, plug it in for a to the k. So I get bk 2 to the k plus c. And then I'm also going to plug it in for a to the k minus 1. Now what I'm going to do is I'm just going to move this whole thing in the recurrence relation to the other side. So I'll move it over here as a negative 2 ak minus 1. So I've got a negative 2. And then what is ak minus 1? That's b with k minus 1 plugged in everywhere I see a k. And that's equal to 2 to the power of k minus 1 because that's the right side of my non-homogeneous recurrence relation. So there's my equation I get by plugging the particular solution into the recurrence relation. And now the method of undetermined coefficients just says, let's figure out what these coefficients b and c have to be in order for this equation to be satisfied. So let's expand it all out. So we get a bk 2 to the k plus c. We get a minus 2 times bk 2k minus 1 minus b 2k minus 1 plus c is equal to 2k minus 1. So that becomes a bk 2 to the k plus c minus 2bk 2 to the k minus 1 plus 2. Oh, I can actually do a bit of simplification here. There's that 2. I can use it to multiply by 2 to the k minus 1 to just bump up the exponent. Same with this 2 in the next term. I can get a b 2 to the k. I get a negative 2c, and that's equal to 2k minus 1. I see that there's some cancellation happening here. There's a bk 2 to the k. That cancels with the negative bk 2 to the k. So what I have is that on this left side, I've got a b 2 to the k, but on the right side, there's just a 2 to the k. Remember, this equation has to hold for all k. So this tells me immediately that b has to be 1. The other thing that I notice is I've got a constant here, the plus c minus the 2c. So that just gives me a minus c, and that's got to equal minus 1. So that tells me that c is also equal to 1. And so therefore, we have found, using the method of undetermined coefficients, a particular solution. It's k 2 to the k plus 1. So we've got our particular solution, we've got our homogeneous solution, so that's enough now to put them all together to get our general solution. So our general solution is a sub k is equal to a 2 to the k plus k 2 to the k plus 1. And now we can go ahead and use our initial condition. So now we use our initial value. What's our initial value? Well, our initial value, at the very top of the page, it's a0 is equal to 0. So that means that I get a0, so plugging 0 in for k here, that's what a sub 0 is. So that becomes a plus 1 is equal to, and that's got to equal 0. So that tells me that a is equal to negative 1. So we've got the value of our constant in our general solution to give us the initial condition. And so we are done now. So therefore, the solution to the initial value problem is a sub k is equal to negative 2 to the power of k plus k times 2 to the k plus 1. And now we want to put it back in terms of n. So remember, n we assumed was 2 to the power of k. That's how we produced our recurrence relation for k instead of using the original one for n. Or in other words, k is equal to log base 2 of n. So we can make that substitution now. So what we get is that when we make this substitution, a sub k, put it back in terms of n, this becomes c of n. What is negative 2 to the power of k? That is negative n. What is k? That is log base 2 of n times 2 to the k, which is n, so that term becomes n log base 2 of n, and then plus 1. Or in other words, our solution is n log base 2 of n minus n plus 1. And there we go. We got the solution that we expected to get. This is the one we got by using the method of iteration, but we got it by rewriting our original recurrence relation for c in terms of n as a recurrence relation for a in terms of k, and solving that first order equation using our general techniques. All right, so that's just a quick bonus video. I wanted to show you that we could use the techniques we had for general methods in this case, as long as we made a subtle observation and converted the equation from the form that it was in, which wasn't a first or second order recurrence relation, but we managed to convert it to a first order recurrence relation. All right, thanks for watching.